So here we've got a pH calculation involving the titration of a weak acid HF with a strong base NaOH. Since NaOH is a strong base, this reaction will go to completion. And basically that's going to be the approach we take to solving this. We're going to have this neutralization reaction go to completion, and based on what's left, we will figure out which type of problem we have of the five primary types of pH calculations. Every titration turns into one of these five. To do this limiting reagent calculation here, we need to know how many moles of HF and how many moles of NaOH. Molarity is simply moles over the volume in liters. If we rearrange and solve for moles, we get its molarity times the volume in liters, and we use that to find the moles of both the NaOH and the HF. For NaOH, molarity is 0.1 molar, and for the HF, the molarity is also 0.1 molar. And we've also got 50 milliliters of each. This is the equivalence point in the titration. 50 milliliters is 0.05 liters. And that's going to get us 0.005 moles for both NaOH and HF. So the equivalence point in a weak acid strong base titration is the absolute worst place to have to calculate the pH here. For a strong acid strong base titration, the pH is simply 7 and life is good, but for a weak acid strong base titration, this is the absolute worst calculation. Now there is one little caveat here. So with a weak acid strong base, the pH will not be exactly 7 at the equivalence point, because the salt we form over here is really a base, and it'll make the solution a little bit basic. And in this case, usually between 7 and 10, and since there's only one answer choice between 7 and 10, that's going to be the right answer. So however, it's not always going to work out that way. So let's work this calculation here. They're both the limiting reagent. They both run out completely. We'll lose 0.005 moles of both of them, but gain that many moles, 1:1:1 ratio here, of our product salt NaF. And so when this neutralization reaction is done, there's no HF left, there's no NaOH left, but we have formed 0.005 moles of NaF. Now, Na here is a negligible cation, but it's F minus here that has an actual base. It is not the conjugate base of a strong acid. But in this case, it's a weak base, and that's the only thing affecting the pH. So this is a weak base calculation. And we're going to need Kb in a nice chart here, or I personally like this lovely shortcut here. That works when you know you're not going to have to use the quadratic. In this case, we can find our hydroxide concentration going that route. So hydroxide is going to equal the square root of our Kb value times the concentration of the base. So we don't have a Kb value. Right now we have a Ka value. So we keep in mind that Ka times Kb equals Kw. So we can figure out the Kb value for F minus. The other side of the coin is we want the molarity of the base, and right now we have the moles of the base. So we have to take this and divide it by the total volume of 100 milliliters, or 0.1 liters, to turn it back into molarity here. So in this case, if you rearrange this to solve for Kb, we see that Kb actually equals Kw over Ka. So that'd be 1 times 10 to the minus 14 over the 6.8 times 10 to the minus 4 value for Ka given. And then do the same thing for the concentration of base. So hydroxide is going to equal square root of 1 times 10 to the negative 14 Kw all over Ka, which again was 6.8 times 10 to the negative 4. So, and then times the base concentration, and it's moles over liters for concentration, so it's 0.005 moles over, again, 50 milliliters, and 50 milliliters is a total of 100 milliliters, which is the same as 0.1 liters. Cool, and from here, we'll calculate our hydroxide concentration. And that gives us a hydroxide concentration of 8.8 times 10 to the negative 7 molar. We can take the negative log of that to come out with a pH. That gets us a pOH of 6.1, and if we subtract from 14, that's where the pH of 7.9 comes from. There's your answer.